Hello everyone, we are Zhong Chaopan and Ziyue Li. Today we will introduce our deep learning journey on the prediction of lung cancer. Our content includes research question and motivation, and also our data exploration and insights, the methodology, the results and evaluation, and also our future work. Well, we all know and recognize that smoking is harmful to our health, and there is a wealth of scientific research and medical evidence that clearly shows the many harms of smoking. However, these harms are often accumulated over a long time period and gradually become apparent. As a smoker, it is difficult for me to immediately and intuitively feel the degradation of my health. However, the pressure I get from nicotine is immediate and intense. This perceived gap between the short-term pressure and the long-term harm makes it easier for us to indulge in the satisfaction of nicotine and ignore the long-term health effects of smoking, even though we are aware of the negative effects of smoking. Therefore, if there is a way to accurately predict the health risks I may face in the future based on my current smoking habits, frequency, and other factors, and to alert and warn me in real time, this will significantly improve my intuitive perceptions of the harms of smoking to push me to quit as soon as possible. To help me achieve this goal, Ziyue searched for datasets that predict the likelihood of lung cancer based on factors such as smoking frequency and used them to train a prediction model. Next, she will use my own smoking data to predict the future risks of lung cancer in the real time and present it to me in a virtual progress bar so that I can feel the threat to my health and be encouraged to quit smoking as soon as possible. We have just mentioned how personalized prediction models can virtually remind us of the health risks associated with smoking and motivate us to quit as soon as possible. In fact, there are successful real-time precedents of using AI technology for cancer prediction. I recently came across the story of Wolf, a medical imaging doctor who posted AI codes on websites that helped detect pancreatic cancer with about 93% accuracy using X-ray images. Although initial anonymous, he gained attention in 2022 by launching a free brain cancer prediction website. It was later revealed that he wasn't a professional programmer, but he spent his spare time building open source health tools using public datasets. He even bought 50 RTX GPUs himself to train the model, aim to benefits to the public. Deeply inspired by Wolf, we would like to imitate his action by training a lung cancer risk prediction model based on personal X-ray images and open source it for free for the public use. We hope that our model, like Cool's project, will allow more people to visualize their health risks, thus helping them to make more proactive and timely decisions to quit smoking and protect their health.
Hello everyone, this is Ziyue Li. Let me now walk you through our data processing and modeling approach in detail, starting with data exploration. We began with the lung cancer risk prediction dataset that contains structured tabular data. No images at this stage. The dataset features both numerical values and categorical entries, and you can see from these left pictures that many of the features were recorded in non-numerical formats, such as the yes or no answers and the scored answers to some symptoms. As deep learning models cannot interpret these formats directly, when converted categorical values into numerical formats. Yes or no were translated into 1 and 0 respectively, and scaled categories like high or low were mapped into integer scales such as 2, 1, or 0. This conversion made it possible to fit the features into a neural network while preserving their semantic meaning. And we also faced a challenge with the country column in the dataset. Country information may reflect environmental or policy-based risk factors, but is difficult to encode with standard integers because doing so would wrongly suggest an ordinal relationship. And to solve this problem, we used target encoding, which maps each country to a number based on the average cancer risk observed for that country in the training set. This technique helps models pick up country-level trends without introducing false orderings or correlations. After transforming the categorical features, we turn our attention to the scale of the data. Our dataset had a wide range of value distributions. For instance, the age ranged from 20 to 90, and the years of smoking might go from 0 to a large number, while binary features were simply 0 or 1. And training a neural network on such mixed scales can cause it to favor features with larger numeric values, even if they are not more important. To solve this problem, we apply two types of scaling. The min-max scalar, which transforms each feature to a value between 0 and 1, and this is useful when we want to preserve the original distribution shape but bring all values into a uniform scale. And the standard scalar, which transforms feature to have a mean of 0 and a standard deviation of 1. This is especially useful when data follows a Gaussian-like distribution. By scaling all inputs consistently, we reduce the training instability and helps the model converge faster. Another benefit of this pre-processing step is that it reduces the influence of outliers. If a single patient's value is far off from the norm, say someone smoked for 60 years, it won't skew the model's gradients during training. Now that our data was cleaned and scaled, and we built our first prediction model, a simple feed-forward neural network, we chose a three-layer architecture consisting of an input layer to accept all features, while two hidden layers with ReLU activation, and a final output layer with a single neuron using sigmoid activation to output a probability between 0 and 1. Since our task was to predict whether someone is at risk for lung cancer, a classic binary classification problem, we use the binary cross-entropy loss function. This function penalizes incorrect predictions more heavily as they deviate from the ground truth, which makes it suitable for the output. And for optimization, we chose the Odom optimizer, which combines the momentum and adaptive learning rates. It's a reliable default that performs well even without much training. Our validation results were promising that validation accuracy reached around 79.9% and the validation loss was around 0.5, which indicates relatively good confidence in the outputs. And this model taught us a lot. Despite being simple, it already captured important relationships between features like smoking history, age, and lung cancer risk. We also tried using Tuna, and the performance didn't improve much. This led us to consider possible explanations. First, the dataset is relatively small, meaning small tweaks may not lead to significant gains, and the feature quality might still be noisy. And lastly, we may have hit the limit of what structured data can do without richer features, like image data or something like that. And to explore richer dynamics, we moved on to a temporal modeling approach. We used a global dataset of smoking prevalence over the past 10 years and aiming to predict the future smoking rates and explore how that might affect future lung cancer incidence. Here we employed a recurrent neural network, which is ideal for sequence data where past information influences the future. And let's talk about our results and evaluation. In our simple neural network model, we achieved a validation accuracy of around 79.9% and a validation loss of 0.5. This indicates decent performance, especially for a first attempt using tabular data. And in our RNN-based time series model, we could successfully track the changes in smoking rates over time and estimate the future risks for different countries. However, we also noted some limitations that the dataset is limited in size and diversity. Imbalanced classes could bias predictions, and our models are currently not optimized for some deployment or clinical use. And to sum up, this project allows us to explore both the structured database classification and temporal modeling through deep learning. Our journey went from the basic data processing to building and evaluating deep learning models, with a strong personal motivation to create something meaningful. And we are excited to continue improving this project, especially by integrating X-ray image analysis into the predict pipeline. And the following part about the X-ray image will be continued by my partner, Zhongchao Pan.
Regarding the prediction of lung cancer from X-rays, we found lung cancer dataset, which contains a large amount of histopathological image data of lung cancer patients. These high-quality medical images are clearly labeled with cancerous and normal tissues, and can be widely used for training, validating, and evaluating deep learning-based lung cancer classification and automatic diagnosis models. However, our current arithmetic power doesn't support the completion of the training task. We will continue use more advanced devices to complete the modeling and training in the future. The more important task for me is just to quit smoking as soon as possible and do more things for my health. Well, that's all we have, and thank you for listening.